Yes, so for today we will talk about OSPF, and in this video we will cover OSPF Fundamental, OSPF Configurations, Default Route Advertisement, Common OSPF Optimizations. Let's get started. OSPF Fundamentals. The open shortest path first protocol is a non-proprietary integer gateway protocol. We have two types of protocols, IGPs and EGPs. EGPs are extrusion gateway protocols in which in that category we have BGP, and for IGPs we have EIGRP, OSPF, ISIS, and WIP protocols. Okay, the OSPF overcomes the deficiencies of other distance vector routing protocols and distributes routing information within single area OSPF routing domain. OSPF introduced variable length subnet masking, which supports classless routing summarization, authentication, and external route tagging. There are two main versions of OSPF in production networks, OSPF v2 and OSPF v3. OSPF v3 supports IPv6 and OSPF v2 supports OSPF IPv4. Okay, and we have LSAs, LSDB, and SPT. LSAs are link state advertisements. And LSA contains the link state and link map. The received LSAs are stored in the local database called the link state database. The LSDB provides the topology of the network. The SPT contains all network destinations within OSPF domain. We have a figure here, 8.1. Let me this topology, and it shows the perspective of the route from R1 and R4. And you have to note that the local router's perspective will always be the route. That is top of the tree. We have four routers, R1, R2, R3, and R4. If we see R1s, so this is the R1s. R1 is on top, the rest of the routers are on the bottom. Similarly, if we see R4, R4 is on the top, the other ones are on the bottom. So, SPT is the shortest path. Okay. So let's discuss about OSPF architecture. OSPF uses multiple OSPF areas within the routing domain, but the main thing need to consider that we have a special area in OSPF that is known as Area 0. Area 0 is also known as the backbone, and all other areas, area 1, 2, 3, 4, etc. go on, should be connected to the backbone area to intercommunicate between different areas. The backbone will advertise routes into the northern non-backbone areas. We have a diagram here. This is the area 0. You see we can define a single interface of a router into specific area and other interface of a router into another area. So here for R1 and R2 interconnection is in between area 12, and the link between R2 and R3 is the area 0, and the link between R3 and R4 is in the area 34. So area 12 will advertise those to their backbone area, and the other will then from a backbone 0, these will be advertised in the area 34. Similarly, area 3, area 34, those will be advertised to area 0, then and to area 12. And for area 0, those are all advertised to other OSPF areas. So, how does the inter-router communication is done? OSPF uses the assigned IPv4 protocol 89. This is also important. They ask sometimes in the interview. And the multicast addresses we have two types, 224.0.0.5 and 224.0.0.6 for DR routers. Okay, these are the multicast addresses are used to possibly reduce unnecessary traffic. Okay, we have these type of packets in the OSPF, and this is their functional overview. We have hello packet, database design or database description, link state, request, link state update, link state acknowledgement. So what is hello packet? Hello packet discovers and maintain neighbors. Once you connect the routers via link and enable OSPF, it will send you the hello packet. We will observe these via lab as well. Let's go to the theory first. Then we have database description. It summarizes database contents. They basically are describing the LSDB contents. And the link state request is the download database. If a router thinks that part of its LSDB is stale, it requests part of a neighbor's DB using the packet type. Like if a router have not received for a few seconds as designated time, the acknowledgement of the links and we have link state update database. This is an explicit say for a specific network link and normally is sent in direction response to an LSR. Link state acknowledgement, the flood acknowledgements, these are sent and response to LSA flooding, making flooding a reliable transport feature. OSPF hello packets. Okay, OSPF hello packets includes router ID within an OSPF domain, authentication options. Usually we have clear text, non or amplified authentication in OSPF, and then an area ID is a 32-bit number, usually we write in decimal. Then interface address mask, interface priority. The router interface priority is used for DR elections. DR elections is done in the multicast type of networks. Then we have a hello interval, dead interval. These are the time intervals in which packets are sent to the routers. If a router does not receive a hello packet within a dead time interval, it considers the other link is down. DR and BDR. BDR is the backup designated router. Then we have active neighbor, a list of OSPF neighbors on the network segment our router must have received a hello packet from the neighbor within the dead interval. Then we observe there are a few states before the OSPF is fully operational. We have down state, attempt state, initial state, progress state, exchange, start, exchange, loading, and finally full state. Down is the initial state of the neighbor relationship. It indicates that router has not received any OSPF hello packet. Attempt is indicates that no information has been received recently, but the router is still attempting communication. Initial indicates that a hello packet has been received from another router, but bidirectional communication has not been established. Two-way is when bidirectional communication is established if a DR or BDR is needed. The election occurs during this state. Start the first state informing an adjacency. Routers identify which routers will be the master or slave for LSDB synchronization. Exchange routers are exchanging link states by using DBD packets, loading the LSRs sent to neighbor asking for more recent LSAs that have been discovered but not received in the exchange state. Full is when neighbors are fully adjacent. So what is the concept of DRBDR? If there are four routers that share the same multi-access network, six OSPF adjacencies will be formed. This is the example of a four routers, and we have four links that needs to be established. And once we use the DRBDR concept, it simplifies the flow of topology with only three neighbor adjacencies. This is initially we have this one without DR concept. After it's we use the DR concept, it becomes like this. Let me share the screen. Okay, so let's go for the OSPF configurations. For the Cisco, we use the command in configuration mode. Router OSPF, then a process ID. It will take you to the OSPF interface. Okay. These are the examples how we use OSPF. Okay, we advertise all the networks under OSPF protocol. This is the network 1, this is network 2, this is network 3, this is network 4, and all are under area 0. This is the method how we will define the OSPF process and the network advertised networks in OSPF. Then we have the interface specific configuration. In the previous we see over the global configurations. It will auto enable OSPF on all interfaces. And if we want to use a specific interface for our OSPF, then we can implement like this. It defines the OSPF process is 1 and area is 0. Okay, we have two further concepts how we can set static router ID and the passive interface. So router ID is auto selected in OSPF, but if we select a static router ID. It helps with troubleshooting and reduces LSAs when router ID changes in an OSPF environment. The command to set a static router ID is router ID, then give this router ID. It will assign the static router ID under OSPF processes. The command clear IPF process restarts the OSPF process on a router so that OSPF can use the new static router. Okay, making a network interface passive still adds the network segment into the LSMDB. But program providers the interface from forming OSPF adjacencies. A passive interface does not send out OSPF hellos and does not process any received OSPF packets. The command passive interface ID under the OSPF process makes the interface passive, and the command passive interface default makes all interfaces passive. To allow for an interface to process OSPF packets, the command no passive interface ID is used. So for neighbor adjacency, we need some requirements to be fulfilled. First is our router IDs must be unique between the two devices. If we are setting static router IDs, we need to make sure that two nodes or devices does not have the same router IDs. The interfaces must share a common subnet. MTUs on the interface must match. If there is an MTU mismatch on interface, the link will stay down. Then we have an area ID must match for the segment. The DR enablement must match for the segment. OSPF hello and dead timers must match for the segment. Authentication type must match. Area type also must match for the adjacency to be formed successfully. So what if we have different hello and dead timers? This is the question you need to answer me in the section. And for the authentication type, if it's not same, it will when they will share the packets and the authentication type and credentials are different, they will not be able to form the adjacency. And same if the area is stub, the other neighbor you want to form must be a stub area as well. Okay, this is the sample topology and information interface confirmation. Okay, we have our routers with loopback IP addresses matching their router IDs. On R1 and R2, OSPF is enabled. R3 uses specific network-based statements. R4 uses interface-specific commands. R1 and R2 set interface as passive. R3 and R4 make all interfaces passive by default, but make GI01 active. This interface verified that the correct interfaces are running OSPF after making changes to the OSPF configuration. The command show IP OSPF interface brief displays the OSPF enabled interfaces. Okay, this is the show IP OSPF interface brief command. It will show you. It will show you the interface with OSPF enabled and PID. The object OSPF process ID associated with this interface, either 1, 2, this is the router OSPF 1, 2, 3, whichever we selected. Then we have area ID, either it is area 0, area 1, area 2, etc. Then we have IP address, then we have a post, then we have a state, either it is a DR, BDR, DR, loop, or down. Then we have neighbors of OSPF routers for a segment that are fully adjacent. And then we have neighbors C, neighbors that are in a two-way state. Let me clear this one. Let's go to the next slide. So how we can verify OSPF neighbor adjacencies? Command is to use show IP OSPF neighbor. It will show you the router ID, neighbors interface priority, which is used for the DR-BDR elections. Then we have the state, either it is a DR, BDR, or DR other role. We have the dead time, the IP address, and the local interface to which OSPF neighbor is attached. The verification of OSPF routes is the command is used is show IP route. OSPF, here is the example show IP route. OSPF, this is the OSPF, these are all connected via OSPF interfaces. And this is our AD value here, 110. Let's go to this next slide. Okay, default route advertisement. OSPF sports advertising the default route into the OSPF domain. The default route is advertised by using the command default information originate. Then we have metric value, metric type, underneath the OSPF process. This must be noted that these commands must be run under OSPF process. Then we have default route topology and confirmation. The orders of each keyword advertises are default route even if it default route does not exist in the router information base. Zip is the router information base. The route metric can be changed with the metric value option. The metric type can be changed with the metric type value option. We have a figure 811 which shows connectivity to other parts of the network by having R1 advertises the default route into OSPF. This is the default route information. This is the area 0 and we have R1 and this is a static route towards firewall from R1. Common OSPF optimization. Almost every network requires tuning based on the equipment, technical requirements, or a variety of other factors. In this section, we explain common concepts involved with the tuning of an OSPF network. Link cost. Okay, this is the metric cost. Default reference bandwidth is 100 Mbps, and if we are using the interface type T1, OSPF cost is 64 for Ethernet 10, and then fast Ethernet, gigabit Ethernet, 10 gigabit Ethernet cost is 1, remains same. The command auto post reference bandwidth in Mbps you have to mention manual bandwidth here, changes the reference bandwidth for all OSPF interfaces associated with that process. The OSPF cost can be set manually with the command IP OSPF cost. Then we have this range. If the value is not changed, a fast Ethernet interface would have the same cost as 10 GB interface, resulting in the poor routing decision. Okay, the cost matters. There we have fast Ethernet, gigabit Ethernet, and we have 10 Mbps bandwidth or traffic flowing through the network. And if we have 100 Mbps traffic flowing through the network, and we have two outgoing or incoming interfaces as fast Ethernet and gigabit Ethernet. So it will depend, it will be defined by the cost, the optimization of our bandwidth utilization and port utilization. How we can detect failure detection in OSPF. OSPF sends hello packets at set intervals based on hello timer. OSPF uses a dead interval timer which is 4 times a hello timer. Okay, this is hello timer is equal to 4. That timer will be 4 cross 4. If a router does not receive a hello or before the OSPF dead interval timer reaches 0, the neighbor state is changed to down. The OSPF router sends out an LSA with the topology change. The OSPF algorithm processes all the routers in the area. Okay, OSPF allows modification to hello interval. This is the command, this is the range. We have a range of, and please note that for the hello timer we have the range in seconds. Similarly, we have the same range for that interval in OSPF, 65,535 seconds. The timer for our OSPF interfaces are shown with the command show IP OSPF interface brief. Then there's the concept DR and VDR elections. Any router with OSPF priority 12255 on its OSPF interface attempts to become a DR. By default, all interfaces use a priority of 1. The router places their router ID and OSPF priorities in their OSPF hello for that segment. Routers then receive and examine OSPF hellos from neighboring routers. If the hello received is more favorable, the router updates its OSPF hello packet to use the more preferable router ID in the DR field. OSPF deems a router more preferable if the priority for the interface is the highest for that segment. If the OSPF priority is same, the higher router ID is more favorable. And as the best practice in the live networks, we use static router IDs. After all routers agree on the same DR, all routers for that segment become adjacent with the DR. Then the election for VDR takes place. The election follows the same logic for DR election, except that the DR does not add is a router ID to the BDR field of the hello packet. The OSPF BDR roles cannot be preempted after the BDR election except for the failure. Determine the interface role by viewing the OSPF interface with show IP OSPF interface brief command. DR and BDR placement. To change DR placement, modify the interface priority or to a higher value than the existing DR has. The priority we can set manually and the range is between 0 to 255. Command is IP OSPF priority, then set the value. Setting an interface priority to 0 removes that interface from the DR election immediately. Pressing the priority above the default value 1 makes that interface more favorable compared to interfaces by default value. To accomplish the replacement in methodology, the OSPF priority for R1 is set to 100. These are the configurations. R2, R3 are left at the default priority of 1. R4 is set to 0, so it will never become DR or BDR. Here we have, this will always be the DR, and for R3 and R2 we have options that it might become BDR depending on the criteria. Then we have the OSPF network types: broadcast, non-broadcast, point-to-point, point-to-multipoint, and loop. Broadcast is one-to-all. Non-broadcast is one-to specific. Point-to-point is one-to-one. Point-to-multipoint is, if this is the network, we have 4 nodes. This will be the point-to-multipoint. And then we have loopback. Default setting on OSPF enabled. Loopback interface is advertised as the host route with /32 subnet. This must be noted that for the loopback /32 subnet is used. Broadcast networks are multi-access in that they are capable of connecting more than 2 devices. RDR is required for OSPF broadcast networks because of the possibility that multiple nodes can exist on a segment. When we have point-to-point, only 2 nodes can exist in this type of network, so no DR is required. Loopback is the OSPF network type. Loopback is enabled by default for loopback interfaces, can be used only on loopback interfaces. The OSPF loopback network type states that the IP address is always advertised with /32 prefix. For loopback, need to remember this. Okay. That's all for today. So what we discussed: OSPF backbone, area 0, then inter-router communication, OSPF packet type, label states, DR, BDR, network statement, interface, specific enablement, passive interfaces, how the enable adjacencies form, interface fields, neighbor state fields, default route advertisement in OSPF, link cost, failure detection, DR elections, OSPF network types, backup designated router or BDR, dead interval, designated router, hello interval, hello packets, interface priority, passive interface, router ID, shortest path 3, and these are the basic commands. How to initialize OSPF process, router OSPF process ID 1, 2, 3, so on, enable OSPF interfaces, then enable OSPF on explicit specific network, how to configure a passive interface, configure all interface as passive, advertise a default route into OSPF. That's all for today. Thank you so much for watching the video.